So basically, before you begin, Andy, try to shout out to Matt is Fun. I love Matt is Fun. So basically, Matt is Fun. Basically, why Matt is Fun is my favorite website. Basically, guys, look at this site here. Matt is Fun. This is Matt is Fun. Guys, basically, I really want them to look at Miko Hello. Basically, I'm looking at this site. This is my mattisfun.com. But I used this site as a child. Like, I was literally a child, like a young man. Like I was even 8 years old, I was 9 years old, in the Biafra. This Matters phone was always there. It was like, look at this. I'm looking at this blank screen, but this is basically a transparent background, but it doesn't. It's not a black background like this one here. It's not a black background, but basically, I think this is see my background here. It's a mask, and I can see my room, whatever's happening in my environment. Basically, it's where the education is going, and that's why I love it. If you don't know why I love it, I'm just implementing my own kind of website system. So basically, it's accessibility by design. So you can really do things like a whiteboard. You can look at and look at your background. So right now, I'm navigating Matters Fun. Matters Fun is literally just the website I'm navigating. You can see everything. Fourier transform, a series of sine, cosine. We've added to make another function. Basically, the accessibility of this legacy website, mattersfun.com, is so groundbreaking. I'm shocked. I'm shocked at it. I'm still happy about it. I'm like, I'm reading text on my screen that you guys can actually highlight for my educational reform. But that's just my gate. Basically, since like me being in the background and learning, but digitally, this is a Muko Hollow system, but holographic learning. So half real, half true. So basically, I can now interact with it, with the kind of interface because it's gonna be instructive. This is what I mean. This is what I mean by education. Basically, I'm thinking of like the zoo system, like have a I come busy. I want me to do my video, but I'm looking at this website, Masters Fun. The background is very black, very black, but it's a strong one I use XSplit. Now I'm using XSplit and VCAM to do it. Now this VCAM is here, but I'm looking at my screen. I can read all the words. I can watch the videos. I feel like I'm actually learning. I can move my cursor on the page. A series is of sine and cosine wave function adds together to make another function. Below is a sine plus sine 3 cube over sine plus 3 5. This is a signal system. The complete series x y. Okay, I know what this means. Basically, this is trying to basically a series of basically a Fourier series. Maps two homogeneous states, sine and cosine, over the inverse row, over the inverse cases. So that's one over sine and one over secant. For dimensions, 3 dimensions. For example, sine x plus a sine y x sine 3x over 3 is a fractional representation of the dimensions x, y, z for modeling analytic systems. But sine 3 is sparse enough. Is sine over sine 3 sine 3 is positive or negative, so you get sine 4, but you get the sine 5 x over 5, which just means the cosine. If you do sine x over 5, you get cosine 3 cosine 3 cosine x cosine x 5, then you get 5 6 7, so you get 3 plus so 5 over x over 5 is 3 over x, so you get sine 3 over x. So this is what I mean. So I can read this. Listen, I'm looking at this website right now on my XSplit. I'm like, oh, so beautiful. I'm like, do you know how I feel? I can actually learn something without being just by looking at it. I'm just reading it. I'm like, beautiful. Like, guys, this is what we need to learn. Gen Z is what we needed, guys. Basically, we have some. YouTube have some whiteboard system, but it's not interactive. So basically, Rift education system makes some ensure the basically if I cannot even learn the interface in my way, just by looking at the screen, I'm not even learning anything. I'm looking at myself then. I'm like, oh wow. Basically, if I can write code, if I'm trying to gossip on the website or write a Rift app, I should be able to just look at it and learn by color coding the text. Because if the text, if the patterns match color code in C, and when you have the R matching syntax, you should be able to have a dimension of seeing, hearing, based on open sense. So get open sense. So get 5 times 5, 25. Maximum dimensions you can access to see. Union, intersect, that are static, and the other one that is non-static. So this is static dimensions that you can always access. You can read, write, execute based on your observation only. And you got the other dimension, which is the this one here. Basically, you got the other dimension. What's the other dimension here? So basically, I'm learning about foreign transfers right now, but I remember my forest series. This is my own one I meant to upload. This is the forest series, OBINexus breaking stone. Now look at my own work, breaking stone. They said, how can I model this foreign transfer over analog? Basically, I'm trying to get see all the basically give a foreign translation, which is the analog equivalent of digital forest space. Basically the bits and bytes that make up the analog signal into from by measuring how the radio hops and how the channel are organized when you model them in digital. So I'm trying to model dimensions as the forest series or forest sequences. Now forest series are easy if you can know what you're doing, but the problem I'm trying to do. The main problem here for me is basically I'm just gonna try to give you the problem and try to define for you how I learn. So if you can even learn it, basically I'm autistic, ADHD, Asperger's, learning disability. This must stop from here. I can't have to go through many websites, many tools just to get some simple thing done. So let me just try to do it for you guys so you can see what I'm looking at. So this is a photograph. Let me try to do it actually. So let me try to do. Should I map the analog? Okay, do you know what I'll do, guys? I'll solve this problem first and I'll see what you guys think of it. So I got this now. So I need this okay, so I'm gonna try to do it radio waves, microwaves, infrared, visible light, ultraviolet, X-ray, gamma ray. And that's just wait, and then we get the visible light, which is the root, visible light or root, which is root red, red. This is EM wave. EM, electrical magnetic duality, can give you red light. So you can measure, you can see you can see all this in red. Okay. V space radio wave, V visible light, is made of red, orange, yellow, which shade of yolk gave green, battle, blue, indigo, and violet. And that's the tree. So I'm just going to this tree. I'm doing my own work on paper too. My medium is paper. I'm using it because I don't have any complicated system using it. I'm just showing you guys the simplest way you can do it. So basically I'm trying to find a transformation, a first transform, a fine transform over sequence. So basically, if you don't guys understand what I'm doing now, I'm going to back to my site. So I'm giving you an example here. If I get it wrong, it's not even a problem. It's about the interface I'm interacting with. So I prefer to put this on my system because I'm using XSplit to do it. Okay. Basically, it's easy to do, but people don't get confused because I know the problem is the definitions. So basically, it's a Frankenstein graph. Basically, this the summation of 1 to 10. 1 or 10. Basically, n is 1, the smallest unit, and 10. So the 10 is it's like 0 to 1, but it's mapped to 1 to 10. 1 to 10. Because if 0 is nothing, then 1 is something. That's how Fourier works. So 10 is the canonical unit we use for modeling the decimal equivalent based on the scientific notation. So example, I'm showing you guys how it works. So block plus minus. Don't worry about this. I didn't even want to read this for you guys. So you get the transformation sine times x over n. So sine wave, any sine wave is equal to echo waves. Basically, so let's get the table here. Sine cosine table. So sine cosine table. So let me go back to my other one. It should just work as intended, right? I know I won't make a mistake, guys. I really know what I'm doing. A bit too much actually. Like this process. So get I'm just trying to find it here. Stop. So the sine cosine table is here. 1. Sorry guys, I don't even know why I'm gonna so I'm trying to make this because I'm trying to find the definition of the sine cosine table. But I'm even looking at the Fourier transform because I know what I'm doing, guys. I'm just basically, this is the video why Fourier transform. Basically, Fourier transforms are dynamic transformations, because of dynamic systems and waves. So they're better for dynamic systems, which have dynamic state. Basically, you have data, canonical data, and canonical data, and canonical functions, which are called functors. If you have canonical data or shared data, all data, that's really all accessible. You can write to all the data. No matter the space is here, you can write to all, you can read, write, execute to all the data based on how it's modeled. You can have 1 over RxWx, read, write, execute, which means you cannot execute that data. You cannot execute it because it's not bound to your system architecture. It's not for you. it's like Windows and Linux duality, problem. So that's basically Windows RS read write execute. It's not what Microsoft Mac intended to implement because they didn't have the idea they can do it that way. Um, so basically, the idea is say like a 64 Zulane use that to teach people. Sister I love Sister Fozu. Imagine Sister Fozu is very good. I love that show. You got all the ones. Dennis Anasha. I love Dennis Anasha. I love Horrid Henry. If Horrid Henry trapped me, I wouldn't be a rebel. I wouldn't be as horrid as Henry to other people. I'll actually be happy with we use Horrid Henry to teach people. I'll be engaging with Horrid Henry. Kind of, but that's what we need, guys. Shows that mirror our reality. Not those things that are abstract and we call them rebels. Because if they showed me Horrid Henry, I wouldn't even know Horrid Henry was horrid. I'm gonna copy him. If the TV wasn't, if they really wanted me to control me, they would just remove Horrid Henry from my life. And then why are you so horrid, Namdi? Or Henry, because I'm Henry. I'm Dennis and Nasha. I'm like Roy. Roy is a good show. Roy was a rebel. He's a vicious man. So basically, you get so when you get sine, you get the inverse, which is sine, cosine, cosine. But cosine has the share a chemical state. So they share the x and the ratio plus 2. For example, sine matrix sine x here is equal to cosine x over 5. Wait, 1 2 is equal to sine cosine. So sine is basically so katoa. So sine is equals opposite of a hypotenuse. That's like y axis. Cosine equals y x. So cosine equals opposite. Co is opposite of a hypotenuse. So that's this is theta opposite angle over the hypotenuse. So that's opposite over the hypotenuse. So basically, cosine here it's this is easy to do, guys. Opposite. I'm going to show you opposite of hypotenuse, and that's cosine. That's measuring the y. So if you're the amplitude on the y, if you're working on any property, amplitude, oscillation, that's cosine. Now, please let me do it properly, guys. Because if I make a mistake, guys, you need to laugh at me in the end. You say, why do you say you can do it? You can't do it. That's what I'm trying to avoid. So basically, the sine table, my cosine table will be so toa. This is basically y is like so that'd be y x to y relationship h. So so opposite so is sine equals opposite of a hypotenuse. Cosine equals opposite of hypotenuse. So get co. So the cosine of x or cosine of theta, because this only plays theta, not x, is the angle. Now the angle can be what theta? The angle can be theta. The theta is the rotation, like a 90 degrees or 180 degrees, some kind of based on 360 rule. 360 is the canonical unit of pi r squared is the area, and the perimeter is 2 pi r. So 2 pi r. So basically, you have a shared theta, which is just a data point, or basically data point, or some kind of scalar, or which is a number, or like some kind of unit model, like a vector or something, to grow the system based on rotation, enlargement, rotation, which is like polar rotation, which is shared rotation, polar transformation, which is x f of x based on the area model and the perimeter model, and they get perimeter and then reflection, like the inverse conjugate, inverse system that models the same thing but its own system space environment, and you get rotation, rotation, reflection, and enlargement, and what, which is also the same as shrinking. You can enlarge by half, and then enlargement, you can scale up, down. You can move up, which is transform. You can move down. You can reflect. You can mirror, you can what? Create. What's the other one? You can rotation. So you can rotate. You can skew. Skew like a basically rotation is the thing moving itself, but skewing is moving its own axis. So that's what the lattice. So lattice comes in. So when you rotate something on a polar system, you are skewing on a polar axis, which is like same for the Cartesian one, vice versa, for the Cartesian modeling. But the Cartesian, the Fourier transform in this aspect it represents the dimension of Fourier space. But when you have a lattice and you use a Cartesian lattice, you cannot you can use a Cartesian with the polar lattice. So that's the idea. That's the problem there. You cannot do that as long, so you have to use a Fourier transformation, which is why we have convolution. Now, convolution is like basically convolution. You got a convolution matrix, which is unit over a times d, a plus b, a c sum d. So what I'm saying to you guys, you get the standard convolution, unit a, but that's the determinant matrix. So ab plus ad plus bd is the canonical one. It's the canonical one, but it is not the canonical one for all the sets of information. So basically, it's the union model. So basically, if we're using calculus, we have to ensure the average is preserved. And what do I mean by that? So basically, you get the averaging. So, for example, AB are data points only, and BC basically AB are heterogeneous and heterogeneous pairs of data. And then you get AD, which is okay. Let me try to do this. You get A times D, which is a unit. A times D gives you AD, and you get BD. But what does this mean? Times doesn't mean anything. So you get plus. You can do plus, plus. Basically, you get the operation first. If you have a system state, the state for it growing can be times plus to scroll up, and that'll be this canonical state for it. So what I'm trying to do now is solve this problem. Times, so you get 4 operations plus minus times the add. So if you want to grow a system state, this is called the union lattice. Now the lattice union for static. So if it's a standard algorithm that has a seed that doesn't grow dynamically, it's basically have a lattice union. And you have the same thing, or you have the inverse of a lattice, which is a 1 over all the union operations of the static space. Space based on time and memory in parallel. And the same thing for 1 over Fouriers, all the Fourier transforms which are analog, analog digital waveforms. So the waveforms are digital, but basically you can't use. Basically, it's much harder to use a static algorithm, static transformation, union, disjoint, and intersection to transform the whole system space. To lens. Basically to compute ahead of time. Basically. Which I call, based on the tree model. So this model I'm saying is what is more coherent because you see what is there, and you don't get lost. You can pause the video, Nandi. 3, 2, 1. Let me do this. It's just my work today. Basically, share my work. This is what I'm doing. I'm showing myself my work. This kind of the thing I want. I don't want anybody to come to me to learn anything, but you come to my YouTube. No matter if you're talking with this video, Namdi, that's what I'm saying. So now I'm giving you what I'm saying. Now, what is the problem here? So you see this Fourier transform series. So you got something called a sequence. A sequence is a homogeneous pair of systems. So basically you get homogeneous first. But you can use the homogeneous first, but it's just harder to use it. It's basically less. It's probably kind of infeasible on the system state. For example, A times D is the standard determinant from you get B times C. But this this is a unit model. But this unit model is fragmented. Basically, you get AB, which is a vector, a vector dimension. So A times B represents what? A tomographic. AB represents basically when you get AB, AD is equal to AA, or by state. So you have AD, you can see all the states of AA, or A times A. You see all the states of D times D. You see all the states of A first, then D, and you see all the states of DD. So what this means, you get power states. So you get DA. If you have DA, you see for DA, same basically the inverse one is DA. So you start with D. DA. I have CD, CB equal to CC, CB, BC, and BD, DB. You see, that's the idea. It's kind of that. So the idea is all of these states have the inverse conjugate, which is 1 over the standard unit over it, over the matrix. So the idea is you have some kind of state epsilon, which is read, write, execute, but you don't want anything to execute after it's been compiled. You know, after it's been compiled, because when you're running code, you run it in linear, but I don't like that. So why would you start with the execution? So you can model this as execution of homogeneous states, but we want to do heterogeneous for now. For example, AD. If I want to start with DD, if I want AA to run, all of AD to be used. So I'm gonna pen. This is really annoying me why I don't have my mouth. Okay, so this is insane. So that's your work family. Look at it. Take a picture of it. 3, 2, 1. So you get, for me to see all the states, I do. If I do A first, A first, A only first. So get AA, DD, AD, DA, 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 and DD. So you get AA. So if AA is illuminated, you get a state of A and A on the roots. But you know, then you get DAD. Then we get D, A or D. But you know, A or D has to resolve A and D. So you should resolve A and D to execute. So you get D on the left and then A, D then A, which is the polarity. So you have to execute D before you can execute A. That's the left root. The right tree, because you know we're using Cisco models. Right tree and then root, and you get AD, A then D, and then that's the model there. And then you get DD, because you know if you have DD again AA and then DD, you know, just to make up the heterogeneous, so you get A. These are just states. DD represents states or nodes. So basically, the 4 digits, 2 nodes, 2 nodes, 2 nodes is one system, one canonical system. So DD, D times D is 2D or 2D or equal to D squared. So that's the idea there. Then you get, or A times A is equal to A squared, and that's basically one. So you get the same thing for AD. D first, then A. So D first, then A. You get A on the left side, on the right side, and then you get A, D, AD, D, A, AD, D, A. And you get on the left side, you get the same thing, but inverse. So if you have DD on the bottom, you get AD, AD, and then AD, E or D, A. Which you get the inverse past pairs, you know, and then you get DD. Now DD is just the same state. D, just the same thing. Inverse A. So now I want to show you what I mean by fractional space. This one, you have to use the internet to yourself to learn. So you got this state, this kind of state, but it shares some what's called hops. Now what are hops? Hops are really basically the Cisco model is instruction bound, but Cisco model is conscious. You just knows everything at the time. So you have one state. So you can have all the space. You know all the space at a time, all the resources. Like you need 32 bytes for something, based on some of them encoding. But you know you can have an executable and lickable format, X lickable format that really just bootstrap Muco OS. So Muco OS, if you want to bootstrap an Elf program, use this model to do it, and you have to know the. So if you have the time to do it, you can use the time. You can take half of one resource, example time, half of your time, to do something, or you can take half of the space. And what that will mean in this model is, so for example, if I do the dimension first. So for example, this share one dimension of space time. So for me to define this ADDA. What does AD mean? Adding time, man. So this is why nine. Oh, I don't even know what it is. Anyway, so as I get, you get AD. So basically, it's like radiomography, but executable on the fly execution. So we don't have like a giant. This we have on the fly, because it really knows the memory needs, which are called look ahead computation. It does job, it allocates the bits and bytes, but it doesn't wait. So basically, it's a breadth first search system. So you have 2 execute paths. For example, if I want to compute the Fourier Basically, this is like the AD matrix. So if I want to complete the radio wave, the Fourier matrix of the transmission, based on this Fourier series, and map all of this to some state of the terminal matrix. For example, x are two inputs, input so input input pathway. So I can have any two execution pathways, but they have to be bound by inputs. So if you start with execution, you have two inputs because the output of two inputs. If the output is two or two, then we can get undefined behavior. Undefined behavior. Undefined behavior. It's kind of like disjoint, undefined intersection and lattice bound polar systems based on the lattice model of sparsity and the sparse plane for polarity via the Fourier transformation or the signal electromagnetic spectrum EM wave. So we can define some kind of artifact node via a halfway rule. So basically, if I half the time, I have to half opposite. So half the time gives you defines half the time of some program means you need double the input. Double the input. That's two inputs. So two inputs double. So example, two inputs of space or bytes. For example, without the Fourier transform even. So for example, if I use the time matrix AD CB of time of half the time, which is dimension of time only, I have to bootstrap this to do this properly. Oh, it's done. Oh, it's not done. It's almost done. Basically, you have to be careful how I do this now because if I make a mistake now, you get to laugh at me. I already know I'm doing, but these are very funny, so I don't know. Basically, I don't know. If you get paper here, so I guess paper is stinking. I don't think it stinks too much. So basically, I'm trying to define kind of Nuco OS bootstrap concept that maps all the data in the unit. I'm going to do it now because it's now or never for the education reform. So it goes paper here now. So I'm trying to find some kind of transformation function via the tree rotation for bootstrapping. So the bootstrapping for the system. So I'm trying to half my time. Which is log n time, a shared log n time. That's a shared log n space. So that'll be for the time, there'll be half the homogeneous time. So that's a share two halves. Two halves will be what? A quarter. Two halves, that'll be a quarter. So the space will take a quarter of the rotation. But that a quarter will be equal to the half of the half, which will be the half of the time. So this will be log n time. So when the space is log n time to load, the space basically if the space is log n, if the space is n, if the time it takes is log n, the space is what? N. So let's just do the n first. So you need n space. You need some space to run. This is just reserved. You need reserved space. Linear basically, or vice versa. So if you want half the time, if you want to use half the space, like say you're in an 86 bit system, you need half the space. You need more time. So basically, that's what you gotta balance out. So what I mean by this, so you get a matrix. So I want half the time, because I'm using. So you define a matrix A, B, C, D, which is the determinant matrix, and you get the inverse, which is 1 over A, B, C, D, 1 over A, B, C, D, which is the time bound. So basically, you're gonna half the time. So to half the time, you have to get AB divided by AD divided by 2, or half of AD. But you can half A by itself, which is half the units, but that's half the input. So you don't want all the full. So you get this is just AD or DA, AD or times DA, D or divided by 2. So you get half AD, half of AD times half of BD times DA, D then A. DA. So basically, you get half of the 2, which is the Fourier. So basically, these are half of the input, half of the space you need, or half of the time you need. So basically, this half time is now equal to half space because you need only some kind of back to the. For example, if I'm storing only if I'm in the electrical, if I'm just downloading some artifact, downloading some, let's say 1 byte, 8 bits, 16 bytes, no. 8 to the power of 8 and 1 byte 1 byte to the power of 16 bits. That's 8 to the power of 16. What would that be? how many bytes? 8 to the power of 16. I think that would be let me calculate that now. 8 to the power of 16. 8 to the power of 16 is 262144. And that'll be what I need to convert to bytes. Let's go to megabytes to kilo. You get megabytes, kilo. You get kilobytes to 1,000. You get megabytes, kilobyte and megabyte. You get this to megabyte. That'll be let's say basically let's say kilobytes. So let's just do 2 kilobytes because that'll be kilobytes, bytes to kilobytes, from, let's just say bytes to kilobytes. Which is 1,000. 1,000 is starting units, so 1 byte equals, let me just put it here. Basically, you get you have to divide it by 1,000, so you get 206,144 kilobytes. Or kilobytes, which is 1,000, 1 to 1,000, 1,000 conjugate. So 1,000 is 3 zeros. So you get 000 or minus 4, minus 4. Because it's used to get and you get 1 over minus 4, 1 to the 1,000 kilo to 4, and 1 over 1 minus 1 and 1 over minus 4, minus plus 4, 1 over plus minus 4. 1 over times, 1 over divide for all the space you're calculating for unit the lattice system. So that's the idea. The lattice system is meant to be there without fragmenting the whole ecosystem for real-time analytics of the system. So basically, this has been done. Oh, it's still going. It's still going. It's still going. It's still going. Oh. So my count should be right. Okay, basically, that's the byte you need. So you really know the bytes. You're doing it parallel. You're not showing the resources because with space and time and resources, you only sacrifice one at a time. You don't use space at the same time. You have basically any half time. So the space time because you don't fragment anything. Because if you fragment the space, if you're using space where you make using time as well, you have to context for it. You have to say, okay, why? Basically, it doesn't matter who's listening, who's sending the message, but if someone needs to be listened to, they need to be listened to now before they get crazy. That's how I like to think about it. Before the start system becomes to decay here and become corrupted. No matter if it's a train, example, if I'm driving by a train and if I'm driving the train and I pass someone, or I forget to pass someone to let someone in, I miss my stop, then we do have no conversation. It's a big problem, I think. It's a big problem in parallel. So we start to lose synchronization via Hamiltonian illustration. So that's the idea there. So this matrix AB CD is the standard of a half. Now the half is a half of time. Is 1,000. 1,000. Now the 1,000 is kilobytes. Is what? Kilobytes. That'll be 260,144 time. So in time, in dimension, in space. Now this is my time. This is the equivalent time I will need to do all my computation over that heterogeneous model. That's all my computation done. Let me just try to get some. This is recording. Yes, that's all my computation done. Let me just try to end this. Stop this because I have to say this. Export. Homo hetero. Education reform. 1. Okay, so basically, now so the idea is literally to ensure that the time passes is passing in a way that can be understood, and processed in parallel for all the operations, using trial model via semantic version extended. That's the idea. So basically, this 200 kilobytes is 1,000. So you get units of canonical world of 10 units, but in binary it's either 1 or 0, so you only have 2 bits. Those 2 states can be at a time and or a time. But depending on the amount, you get AND operation. And so basically you get or and, which is like decimal, and which means plus or minus. So you get the canonical decimal, or the canonical which is computer tripartite. So you get, so if you have 3 bits, you get you have the states of 0, 0, 1, 1, 0, 1, 1, 1, 1. But and then that's just the first one, because if you then if you start from the left and it's a 0, so you get the parity bits. You get 3 canonical states. So if you have 0 and a 1, 0 and or 0, this is the same thing as XOR. So you get or. So you get if you do or first and then or, you get and. So or equals and, but for higher systems, high or and XOR, which is exclusive or for the input of 0 and 1. So even a 0 and I think it's a 1, that's really fragmented if I don't know whether I mean yes or no via consent. Not via consensus, because consent is the first protocol of negotiation. Permission needed. So if I put a 0 in, and if I put a 0, if I'm talking to someone and I see a 0, if I see a 0, if I expect a 1, and I go, if I put a 0, I expect a 1, then that's almost like a 0 or 0. If I still 0, or if I still 0 or 0, if I put a 0 and I go a 0, it's basically 2 more 2 inputs. So 0 0 is A, 0 0 1 0 1 matrix. So that's AD BC. So if I do 0 and I multiply by 0, that's an all state of 0. That's like correct. If I do 0 and then 1, and I'm expected to get a 1, I get a 1 and get an exponent of 0. And then if I do 0 times 0, that is not 0. And again 0 times 1, 1. Again, basically you get all the pairs 0 times 1. So the same thing, you get 0 1 0. You get all the, you get AD times BC. So you get AD is what? 0 times 1 is 1 1. Because if I expect a 1, I get a 1. 0 times AD, A times Z is 1. B times C is 0 0. So you get 1 0 1 0. So if I do AD, if I do 1, so 1 over 1, so 1 times 0, you get so you get 1 times 0, but you get 0 1 times 0 1, and that'll be 1. Carry the 1, that'll be 1 1. So you get it's 1 1, 1 1, and then you get AD 1 1. But we don't always expect 1 1, and then AD, which is equal to D, AD, or DA, or DA in the inverse one, in the opposite, in the polar opposite, and you get the 1 over for the conjugate system, 1 over AD BC example. So basically you get that half the ratio of time, and then you get AD, that's AD BC, AD for BC, and then we get BC, which is 0 0, because 2 share 2 states of 0 0 with the parity bit. So parity bit is just the third state, third 0, third binary 0. So you get 0 0 1. If you have nothing, the parity bit can be 0 1. It can be 2 states. We don't know the state to resolve it. So it's like a fourth one is Byzantine network for consensus modeling, which is with 3 bits. So you get 0 0. So you get, for example, so if I get AD or DA, I get BC. So BC will be B times C, and that will be 0 0 times 0 1, and that will be 1 0 0. So you get 1 0 1 0. 0 1 from the left is CD, BC, and you get 1 1 1 1, which is 1 1 is 1 times 0 0 0 1. That will be 1 times 1 is 1. Carry the 1, and that will be 1 times 1 is 1, which is 1, and 1 times 1 is 1. So you get 1 1 1. So that's the full 1 1 1, and that's the state space. So you get Basically the epsilon state is not one here because that epsilon state is a canonical nil. So we shared a shared unknown, shared known, shared unknown, and what shared known, shared unknown, and shared unsure state. So we know it. Well, yes, we agree we know it. No, we don't agree we know it. And we have the consensus model here. So we have this consensus. We're not sure what the message means or the packet is. But I did say this video is going to be the core system. Next one I'm going to make. Anyway, so the core system is really spring bound. So if I get some that max basically coil basically get a resistor coil. So if I'm polling just means listening wait for connection. So I can be waiting, but I have to listen. Basically, I see everything that's happening, but I'm not doing anything. Basically, I can observe but not act. That's like polling. So if I'm doing something, if I'm touching something, if I'm feeling something, I'm observing my sensation, my surrounding, but I'm not actually doing something. I'm not actually acting something. That's kind of like because I'm not polling. I'm polling. Basically, it's just the reverse proxy. So if a proxy is listening, active listening, basically if a proxy is like active listening, this is like a silent listening, a non-active listening. So the protocol is non-active. It's static. It's a static protocol that's stateless. It just observes before it acts. It doesn't need to do anything. It doesn't need to. Before you form the system. So if you get the parity beat model, yeah. So you get the AND state, the canonical AND for this, and then you get the same thing. You get AND O, which is XO. You get OO, and then you get mechanical and OO, and you get the for the O for the XO, which is which is exclusive O. We take the same state, as XO, which is you just exclude the bits. These are ones, the tens are epsilons. You get your information, only information you need to store it in the diagram via CNOT. CNOT gate is quantum bound. So the CNOT gate is responsible for quantum computers via the XNOT port. And they can execute it. Now, the execution is very important to do because execution is like running the code. So if you can build it or the library, just stop at the CNOT model, and that's really the system half built. Just like half built in half time, and you have the half space done. So it's really half linked. Via that's the idea. You half the time and have the space and time. So you have the CNOT gate half, it's half space time. So the programming runs but half the time. Now, when you now have the program, it's built, it's compiled, it's built or compiled, but it's not run, so it's not executed. So if the program takes half the space, it can take half the time as well. So basically, you have to have some kind of a shared IOTA state of one for execute. So the IOTA state is just the first transformation. Basically, before I go after this problem, so you get the first transformation. I'm going to more people right now. So basically, the first transformation is going to so you get the first transformation. Okay, so what do you mean by that? You get the first basically. You want to basically say you're saying you speak to dialect. So if you're speaking to Python, you speak to Python or Lua, you are speaking to one line dialect. Now that one dialect is just one dialect. You don't even need to tell it what to do. It's like speaking to someone and you don't want them to listen. You just want them to listen. You speak to someone, you don't want to run anything, yet you give them the permission, the consensus to run, but on their terms, on their protocol. Basically, for on the fly. So whenever they want to run it, they give themselves consensus. You give them all the consent. You have a shared state of consent, but you give them polyglottic build. So you give them the permission to build it on their consent. That's the idea. You give them consent to share the protocol, the A star scoring, A star time, space time, which is O of 1, log n over log n, compute time equals O of 1, and you give them that model to. So basically, you can if you execute your one, you execute for yourself. You link and execute for yourself, which is called a linkable format, which is shared format. So link and then execute for your own GOSILANG file, GSI interpretation. So the instruction layer will be polyglot. So this will be Python Lua. So when you have an interpretation, a message packet, which I call a coil packet, you send it through the Fourier transformation, and this Fourier will be with the analog wave in the electromagnetic spectrum. Formally, but the idea here is the message Gaussian JSON file is linkable. So you create enough gossip G for golf, S for Sarah, N for Mike, which is a message to Python and Lua that is canonicalized And when you are then gossiping in the go G for goat, S for Sarah, I for indigo or ink, because I love this duality. You are literally interpreting in Python Lua for whatever your operation. So Python does its job in its dialect, and Lua does its job in its dialect. The protocol is stateless, the data is sparse, the lattice usually there's no dynamic solution. If Python needs anything, it just goes to Python, just only talks to Python. It doesn't never need to reach out via monoglot if it is. If it is just a monoglot, polyglot, if it's or hybrid, if it's just a polyglot, if it's just a hybrid, which is chemical state, iota state, you can if Python wants to speak to Lua, it's then set a iota hybrid. But if you want to lock it down, you lock it down on monogon, Python to Python, lock it down to hybrid. Hybrid means like a shared Python to Lua or GOSILANG if you want to do that, and then polyglot all the systems. That's the idea. Because you don't need to fragment an ecosystem to rebuild it, which I hate. So this is an ecosystem that's stable, because you just tell it what you want to do. You just speak to it in the most canonical state, and it does it. It listens, but based on the canonical reliable interpretation of the system state. That's why I'm building. So you get the GSX. Now, gossip, G for gossip, S for Sarah, and X for execute. This is execution layer for GOSILANG. So this is IOTA state for GOSILANG running in GOSILANG. But you can put the GS files, but the I, X, and X M states are message packets. Message packet is literally, I haven't got more space here. A coil. But I'll come back to that video next. So what's a coil? A coil is a packet that's a tripartite packet based on this path. So you get a state of 0, 0, 0, 0, or all the way to 1, 1, 1, for each state. So you get 0 or 1 measures. So you get a dimension of 3, of 3 by 3, 3. So you get 0, 0, 0, 1, 1, 1, 0, 0, 0. You share a shared epsilon state, EEE. You get 0, 0, 0 for off. And 1, 1, 1. Well, so basically, you can literally just model a computer turning on, computer turning is off on, basically, you can get a computer to turn, to switch to a context to turn another computer on, no matter where you are. Basically, if I tell my friend's computer for him, I log into my computer and type, yes, turn it on. I give him consensus. He gets verifies his computer's not working. I turn it on, you start working. That's kind of the thing I want for myself. So that's the idea, 0, 0, 0, E, 1, 1. And that's what I want, based on the Bobby Collier pi r squared radius. And that's what I'm saying. So the epsilon state is canonical, or shared canonical, or parity canonical, so how will this actually work? So if I was shared iota state, so, I will put this video out, but let me just get more people. Kind of like I'm wanting to, because I really just spread the paper for no reason. So what do you mean is you get so you get a shit, so you get E3. So yes, we it's basically if yes I'm sure or no I'm yes or no. This is E. This E means I'm not sure. So I'm not sure, but I know I may be right or you may be right. So for example, E equals yes yes. So if you want to polarize E2, so E has two poles, a positive sure, positive I'm sure, or negative I'm not sure. But you're not sure is my sure. Sometimes my not sure is your sure, not your sure, not you're not sure. So basically, right if I'm sure, right, root left, sure, right, root left, and that'll be sure. Oh, this is for trying more. Okay, sure. If I'm sure, then have another state of am I sure? Yes, I'm sure. Or no, I'm not sure. That'll be then go to the other one, root, and then yes, I'm sure. No, I'm not sure, and then all share a state of epsilon. We are unsure. I'm unsure. I am unsure. I am sure. No, I'm sure. I'm sure. I am not sure. I am not sure. This will be E plus E minus the plus E plus E minus the plus E, and you get plus so minus E minus E. So basically, you get the same state for all the sparse model based on epsilon resolution. So example, so what this means, you get epsilon state. If I'm right, sure, I'm unsure. So I'm unsure. But that also is like a positive epsilon, a shared positive epsilon. We both epsilon squared negative epsilon, a plus, plus then minus epsilon, and epsilon minus epsilon. Epsilon, negative epsilon to positive epsilon squared, and that's the ideal state of that system. Based on uncertainty, which is called what I call ontological evasion, which is probability. Probability by computational probability, because the system already knows the state ahead of time to continue the Bayesian computation of arbitrary systems, since that it doesn't really understand yet. Which is arbitrary. So basically, arbitrary means system is understood. So, basically, a Fourier series is the same. A Fourier series is basically the substrate or the substructure. Basically, it's the superstructure. It's basically all the structure of all the homogeneous and heterogeneous structures of a sequence. Now, a sequence is the half structure. So basically, half the time is a sequence, and that's a sequence. So basically, anything that does half the time, half the dimension, can be won by binary sequences, and that would be 0 and 1, but they are mangled and wrangled at the same time. So the wrangling is what I call. So you want to mangle everything. You never want to wrangle it, so you mangle it, you wrangle it. So wrangling means you basically you make it fragmented, and that's the idea. Because you want to mangle or wrangle, you have to separate so you can understand it, but no one else on the system can. Via the protocol of GOSILANG. Thank you guys very much. But the Fourier series are like canonical systems. A Fourier system can represent a digital waveforms and analog waveforms, and that's why they are because you can have digital. If you have full, you either have digital or analog, one or other. Thank you very much. Based on how you use it, like physical hardware or like or plugs or anything. That's how you use it. Thank you guys.